Hello, my name is Kavita and my paper is on min-cost popular matchings. Our input here is a bipartite graph where every vertex has a strict ranking of its neighbors. This is such an example. The numbers on edges denote the ranks a vertex assigns to each of its neighbors. 1 denotes top choice neighbor, 2 denotes second choice neighbor, and so on. Such a bipartite graph is also called a marriage instance, and this is a well-studied model in two-sided matching markets, and it's used in applications such as matching students to schools and doctors to hospitals. What one typically seeks here is a stable matching. A matching is stable if there is no edge that blocks it. The blue matching here is unstable because the edge between the two middle vertices blocks it. However, the red matching is stable. Gale and Shapley in 1962 showed that stable matchings always exist in a marriage instance, and one such matching can be computed in linear time. Stable matchings are very well structured. Their polytope has a linear size description, and this translates to efficient algorithms for many stable matching problems. However, stability does have its drawbacks. There may be exponentially many stable matchings, but all of them match the same set of vertices, and the size of a stable matching may be only half the size of a maximum matching. Can we relax stability a little so as to obtain a larger pool of feasible or admissible matchings? Popularity is a natural relaxation of stability. The ranking a vertex has over all its neighbors extends naturally to a ranking over all matchings as follows. We say vertex U prefers matching M to matching N if it prefers its assignment in M to its assignment in N. Now we can compare two matchings M and N as follows. We'll ask every vertex which of these two matchings it prefers and count the number of vertices that prefer each of the two matchings. And the matching that has fewer vertices that prefer it is the loser in this election. So let's see it on this example. Let's have an election between the red and blue matchings. The top two vertices are indifferent between these two matchings. The two middle vertices prefer the red matching and the two bottom vertices prefer the blue matching. So this election is a tie. Each matching is as good as the other. Let's hold another election between the red and green matchings. Here the red matching is the winner. It has 4 vertices that prefer it, whereas only 2 prefer the green matching. So the red matching is better than the green one, and so the green matching is not really interesting to us. This is a well-studied notion in social choice theory. A candidate who never loses an election, that's a weak Condorcet winner. In the setting of matchings, a matching M is a weak Condorcet winner if M is undefeated by all matchings, that is delta M comma N is at least 0, where delta M comma N is the difference between the number of vertices that prefer M and those that prefer N. Let's call any matching that is a weak Condorcet winner a popular matching. So by definition, popularity shifts the focus from veto power to collective decision. Gardenfors introduced this notion in 1975, and he observed that every stable matching is popular. And in fact, every stable matching is a min-size popular matching, and there are efficient algorithms to compute max-size popular matchings. However, the min-cost popular matching problem is NP-hard. In contrast, there are many polynomial time algorithms to find a min-cost stable matching. So relaxing stability to popularity has come at a price. We've lost the computational tractability associated with stable matchings. So let's ask the question, is there a fast exponential time algorithm to find a min-cost popular matching? In fact, we already know one. There is an O star 2 to the n running time algorithm to find a min-cost popular matching in a bipartite graph. So this paper did not particularly address the min-cost popular matching problem in bipartite graphs. It showed a singly exponential time algorithm to decide if a non-bipartite graph has a popular matching or not. And as a subroutine of that algorithm, we get a 2 to the n running time algorithm for mean cost popular matching in bipartite graphs. So the question we look at is there an even faster exponential time algorithm for mean cost popular matching in bipartite graphs? A min cost popular matching is also NP hard to approximate within any multiplicative factor, And this is the case even when edge costs are restricted to be either 0 or 1. So let's ask the question, can we come up with a natural notion of approximate popularity such that we can efficiently find a low cost, approximately popular matching? Our results are as follows. We show a min cost popular matching can be computed in O star 2 to the n over 4 time. We introduce a notion of approximate popularity called semi-popularity. A matching is semi-popular if it is undefeated by at least half the matchings in G. We show we can efficiently compute a matching that is with high probability and almost semi-popular matching whose cost is at most twice the cost of a min-cost popular matching. And in fact, this algorithm needs edge cost to be non-negative. No such restriction is there for our exponential time algorithm. We use the NP framework of popular matchings. It will be convenient to view any matching as a perfect matching. So let's augment G with self-loops and add self-loops at unmatched vertices in our matching so that it becomes a perfect matching. Given any matching M, we can define a corresponding edge weight function, weight subscript M, that's defined as follows. For any edge AB, if the edge blocks M, let's assign its weight to be 2. If both A and B prefer their partners in M to each other, let's say its weight is -2, otherwise its weight is 0. And the weight of a self loop is defined as given here. Observe that for any perfect matching M, any perfect matching N, its weight under this edge weight function is delta n comma m. Recall that delta n comma m is the difference between the number of vertices that prefer n and those that prefer m. So matching M is popular if and only if every perfect matching has weight at most 0 under this edge weight function, weight subscript M. Let's look at the LP that's dual to the max weight perfect matching LP. This is a simple LP. The dual variables are alpha u's, and the constraints basically say every edge should be covered and every self loop should be covered. A matching M is popular if and only if there exists a dual feasible solution such that sum of alpha values is 0. This follows from LP duality. Moreover, the total unimodularity of the system implies alpha is integral. So let's just outline the 2 to the n algorithm for min-cost popular matching that follows from recent work. This algorithm essentially goes through all possible values for a witness vector. In fact, it doesn't really go through all possible values, it goes through all possible parity combinations. So for each vertex u, alpha u is either 0 or plus or minus 1. It is alpha u is either even or odd. There are in total 2 to the n such parity combinations. For each parity combination I, it asks for a min-cost popular matching in G that has such a witness that is among all popular matchings in G that have a witness whose parities match with I, can we compute a min-cost popular matching efficiently? And it shows, in fact, it can be efficiently computed by posing it as a stable matching problem in a new instance, GI. So among the 2 to the n many candidates that we have found as stable matchings in these new instances, the least cost such stable matching maps to a min-cost popular matching in G. So we extend this algorithm. We show that rather than going through 2 to the n many parity combination, it suffices to go through 2 to the n over 4 many parity combinations. As a first step, we improve this to an O star 2 to the n over 2 running time algorithm. This uses the idea of popular edges. Let's call an edge E popular if there is a popular matching that contains it. Let E0 be the set of all popular edges in G. Let's call the subgraph whose edge set is a set of popular edges, the popular subgraph of G. So the set of popular edges can be computed in linear time, so this subgraph can be computed in linear time. Let's look at this subgraph. This need not be a connected graph. It has various connected components as in this picture. There are isolated vertices as well. An interesting property is the following. All vertices in the same connected component in the subgraph have the same parity of alpha values. So for all vertices U in a particular connected component C, It's the case that all values, all alpha values are 0, or every alpha value is 1 of +1 -1. For every isolated vertex in this popular subgraph, it's the case that its alpha value is 0. This follows from complementary slackness. So rather than regard individual vertices as our atomic entities or units, it's more efficient to regard connected components in the popular subgraph as our units. So for any non-trivial connected component in the popular subgraph, let's look at all vertices in it as one entity, as a whole. And all these vertices have the same parity of alpha values. So it's the case that either alpha u is 0 for all u, or alpha u is in +1 -1 for all u. So we have at most 2 to the n over 2 many parity combinations corresponding to whether alpha u is odd or even for all vertices in this connected component. And this leads to an O star 2 to the n over 2 running time algorithm for the min cost popular matching problem. Our main technical contribution is the following, that it's in fact sufficient to regard connected components of size at least 4 as our atomic units. So we basically do not commit the alpha value of vertices in connected components of size 2. And it's easy to argue that there is no connected component of size 3 in the popular subgraph. So we just consider connected components of size at least 4. And for each such connected component, we go through the 2 options, whether alpha values of all vertices in it are odd or even. And so we have 2 to the n over 4 many possible parity combinations. And this leads to an O star 2 to the n over 4 running time algorithm for the min cost popular matching problem. More precisely, this leads to an O star 2 to the p running time algorithm for this problem, where p is the number of connected components in the popular subgraph of size at least 4. So the 2 to the n over 4 running time algorithm works as follows. For any vertex in a connected component in the popular subgraph of size 2, we do not fix the alpha value. So alpha u can be any of the 3 values 0, +1, -1. For larger connected components, as we said, there is no connected component of size 3 here. So for connected components of size at least 4, we do the following. Let's take a subset of indices. These correspond to selected components. Here the blue ones are the selected components. And for all vertices in a selected component, the alpha values will be either +1 or -1. And for the remaining vertices, alpha values will be fixed to 0. Our goal is to compute a min cost popular matching in G that has a witness whose parities are exactly what is given here. So for vertices in connected components of size 2, it can be anything. And for vertices in selected connected components, alpha value should be either +1 or -1. For the remaining vertices, it has to be 0. So our goal is to compute a min cost popular matching in G that has such a witness. And we'll pose this as a stable matching problem in a new marriage instance Gi and compute an appropriate stable matching in G sub I. So the construction of this graph Gi is quite elaborate and involves many details. So for the sake of this presentation, for the sake of conveying the main ideas, I think it would be best to focus on the O star 2 to the n over 2 running time algorithm from min cost popular matching. So here, the algorithm is simpler. We just take any subset of 1 to k, where these are the connected components of size at least 2 in the popular subgraph. And for vertices in selected components, alpha u is either +1 or -1. For the remaining vertices, alpha u is 0. And we wish to find a min cost popular matching that has such a witness alpha. For that, we construct this new marriage instance Gi. Let's first partition the vertex set of G into S0 and S1. And the vertex set Vi is defined as given here. It has 3 vertices corresponding to every vertex in S1. U plus and U minus correspond to the 2 possibilities of alpha value of U being +1 or -1. And there's also this vertex Du, which is a dummy vertex. It has only 2 neighbors, U plus and U minus. And its purpose is to ensure that at most one of U plus U minus is matched to a real neighbor or non-dummy neighbor in any stable matching in Gi. For every edge AB in our edge set, the edge set EI of this new instance GI will have one or more of the following edges. Yeah, this looks a little cumbersome. So depending on where A and B are, whether both are in S0 or one of them is in S0, the other is in S1, or both are in S1, we'll have a few of these edges in the edge set EI. We also need to describe the preference orders of vertices. The preference orders of vertices in GI are absolutely faithful to the preference orders in G. U plus and U minus have a new neighbor here, du, and U plus regards it as its last choice neighbor, and U minus regards it as its top choice neighbor, and D regards U plus as its top choice neighbor and U minus as its worst neighbor. It has only two neighbors. And edge costs here are inherited from edge costs in G. So this is our first technical theorem. Let's look at any stable matching in this instance GI such that N avoids all edges between a subscript plus vertex and a subscript 0 vertex, and all subscript minus vertices are matched in N. Then N can be mapped to a popular matching M in G whose cost is the same as the cost of N. So the matching M is defined naturally as given here. Just ignore the subscripts of vertices in N. So ignore this SA, SB and the resulting matching. The resulting set of edges is M. It's easy to show that M is a matching. Moreover, M is a popular matching. And we prove its popularity using a witness alpha as given here. For all vertices in S0, alpha U is 0. And for vertices in S1, we take alpha U to be +1 or -1 based on which of U plus U minus is matched to the dummy neighbor. So we just defined a vector alpha. We need to prove that this is indeed a witness of M's popularity. That is, alpha is dual feasible. If you recall the dual LP that we defined some time ago. So that is really the most technical proof here. We use the fact that N is stable in GI to prove that all edges are covered. That is, alpha A plus alpha B is at least weight subscript M of AB. This is a rather involved proof. The converse of this theorem is also true. Let's take a popular matching M in G with a witness alpha whose parities agree with I. Then there is a stable matching N in GI whose cost is the same as cost of M, such that N avoids all edges between a subscript plus vertex and a subscript 0 vertex, and all subscript minus vertices are matched in N. So here we need to come up with subscripts to attach to vertices, and these subscripts are essentially given by the alpha values. Corresponding to alpha U being +1, -1, 0, we'll define SU to be plus minus 0, and N is defined as given here. Just attach these subscripts SA, SB to AB for every edge AB in the matching, and we also need to include appropriate edges incident to dummy vertices, and that gives us a matching. Why is this a stable matching? So we use the fact that alpha is a witness of M's popularity. So it is dual feasible. It satisfies all those edge covering constraints to show that N has indeed no blocking edge, that it is a stable matching in GI. So we showed a sort of equivalence between stable matchings in GI that avoid certain edges and popular matchings in G that have certain witnesses. So the last task is to find a min-cost such stable matching in GI. So we need to check two things. The first is that all subscript minus vertices are matched in stable matchings in GI. This is easily accomplished by running Gale-Shapley algorithm in GI. And the second part is to find a min-cost stable matching in GI with forbidden edges. It includes none of these edges between a subscript plus vertex and a subscript minus vertex. And such a stable matching can be computed in polynomial time by optimizing over a face of the stable matching polygon of GI. So the last part is on semi-popular matchings. Recall that a matching M is semi-popular if it's undefeated by at least half the matchings in G. So let's assume edge cost to be non-negative. Our goal is to find a low-cost semi-popular matching efficiently. And here we'll use a min-cost popular fractional matching. Such a matching can be computed in polynomial time. Moreover, it's half integral. So we can write Q as a convex combination of M1 and M2 as given here. So it follows from the optimality of Q that both cost of M1 and cost of M2 are at most twice opt, where opt is the cost of a min-cost popular matching. Moreover, one of them, at least one of them, is semi-popular. However, we do not know how to efficiently test which of these two matchings is semi-popular. So we know one of these two is a matching we desire, a semi-popular matching whose cost is at most twice opt. However, which of these two it is, we do not know how to efficiently decide that. However, we can decide with high probability if one of these two is far from being semi-popular, in which case the other one is a desired matching. And we'll do this using the result by Jerome and Sinclair on sampling matchings from a distribution that is close to the uniform distribution. So we are given an epsilon. Let's produce a small sample of matchings from a distribution that is close to the uniform distribution in total variation distance. And let's test each of M1 and M2 against all the matchings in the sample and return the matching in M1 and M2 that is undefeated by a majority of matchings in the sample. It's quite straightforward to show this theorem that with high probability, the matching return is almost semi-popular. So a couple of open problems. Can we show an even faster exponential time algorithm for min-cost popular matching? And is there an efficient algorithm to compute a better bicriteria approximation algorithm? Compute a better bicriteria approximation for min-cost popular matching. Thank you.